All right, guys. So we've been taking a look at Laplace transforms and in the context of operations that you can actually perform. There's one very important one that I want to cover right now. So we're going to continue along with our discussion of operational transforms. We did find that if you take the Laplace transform of a constant times a time domain function, you can pull that constant out and just find the Laplace transform of the function itself. We also found that the Laplace transform is linear with regard to addition and subtraction. So suppose that you actually had the following Laplace transform that you wanted to find. Well, you could actually find the Laplace transform of each one of the pieces individually. And then in the Laplace domain, just add the pieces or subtract the pieces individually like this. This whole set of arguments also meant that the Laplace transform as a functional transform, it is a linear one, right? Uh, the next one that we want to take a look at is, and this is the interesting one. This is one of the reasons why the Laplace transform is useful to begin with. We're actually going to take a look at differentiation. So suppose that we actually had a function f of t, then consider, well, suppose that I try to find the Laplace transform of f prime of t, like this. Right? There is an extra piece of information that we actually need. We need to know what the initial condition is. So we're also going to be given, so we're going to assume that the initial value of f of t at t equals 0 is f of 0. And we're also going to assume that f of t is continuous piecewise smooth and of exponential order. And you'll see what that means and the consequences here in just 1 second. Right. So suppose that we actually had considered the derivative, the Laplace transform of the derivative of f of t. Right? In other words, another way to write this in terms of notation, this is df dt like this. Well, by definition, we know that this is the integral from 0 to infinity of e to the minus st times df dt dt. Right? Now, some of the previous tricks that we had done in finding various Laplace transforms of functions uh, included integration by parts, and that's exactly what we're going to do here. Right? So what we're actually going to do is we're going to take this thing, and as a trick, we're going to integrate by parts. And in this integration by parts, I'm going to let u equal e minus st, and dv be df dt dt. Well, if that's the case, then the u is going to be minus 1 over s times e minus st, and v is going to be f of t alone like this. So if I'm finding the integral of u dv, well, this is uv minus the integral of v du. Let's actually assemble the pieces. In fact, let's actually even go back to black. So here, the integral from 0 to infinity of e to the minus st df dt is, well, it's uv, which is e to the minus st f of t, and I'm going to evaluate at 0 and infinity like this, right? Minus the integral from 0 to infinity of v du, which is minus 1 over s. Oh, I'm so sorry. I did make a mistake once again. When I take the derivative of e to the minus st, it is minus s e to the st. So be slightly careful. So this is now minus s times e to the minus st times f of t dt like this. Right? Now, in this particular case, one of the things that I'm going to do is I'm going to take a look at this, right? Because it's an improper integral, since the top bound is infinity, one of the things that I can actually do is for the top bound, I'm going to say, I'm going to take the limit as t approaches infinity of e to the minus st times f of t. And for the lower bound, there's no problem, right? Because I'm actually going to end up plugging in 0. And this is a really critical part. So for the bottom part limit, this is e to the minus s times 0. And I'm going to plug in also f of 0. So this first term is the same thing as this term, right? I'm evaluating my bounds. The second part is, well, notice that you have two minus signs there. I can cancel them out for a positive time, positive one, and notice that s is not being integrated over, right? So I can actually pull it out of the integral, in which case I get s, the integral from 0 to infinity of e to the minus st f of t dt, right? Now, this is where the assumption, and it is an assumption, the assumption that f of t be of exponential order comes into play, right? By exponential order, we mean that this portion right here actually disappears, right? That's what of exponential order means. It is required that that itself goes away. So as t approaches infinity, e to the minus st must decay faster than f of t actually grows, right? Now, there's some functions for which this is true. There are some functions for which this is false. So most functions that we've seen actually obey this principle, right? We even talked about, for example, like the limits uh, as t approaches infinity of e to the minus st times the sine and the cosine and things like that. And we argued that that actually did end up disappearing. There are other functions that do actually grow faster as t approaches infinity, then e to the minus st actually decays. So, for example, a function for which does not work, so if you had f of t being something like this, which you would never see in a real problem, this itself is not of exponential order. The uh, Laplace transform does not exist, right? But If it's of exponential order, then that portion does actually disappear. And the second part is nice and easy. Well, e to the minus s times 0, that's 1. And you multiply by f of 0, well, that's just minus f of 0. So I can keep on going with my calculation and saying, well, this is f of minus f of 0 plus s. And hopefully by now you've seen this often enough. Does anyone recognize that? Well, that's the Laplace transform of f. So this right here is the Laplace transform of f of t, which means that our full result, our conclusion, is that the Laplace transform of the first derivative of a function is minus the value of that function at 0 plus s times the Laplace transform not of the derivative of the function, but the Laplace transform of the function itself. And this is a massive, 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 massive conclusion, right? Now, one question naturally arises, well, what about higher order derivatives, right? So let's take a look at the second derivative. This is another second derivative. So suppose that we actually had the Laplace transform not of the first derivative of f, but suppose the Laplace transform of the second derivative, right? Well, what would that actually become? Well, it turns out to be relatively easy. We've already done the hard part. We've already done the heavy lifting. So suppose that we let a new function be g of t, and say that that is the first derivative of f. Then, one of the things that we could definitely say is that the Laplace transform of the second derivative, well, would be the Laplace transform of the first derivative of t, right? But according to what we just had as our conclusion, the Laplace transform of g, and I'll do this in red, but the Laplace transform of g is the value minus the value of g at 0 plus s times the Laplace transform of g t itself. So we can actually use this in the following manner. We can then go back and say, well, the Laplace transform of the second derivative of f is the Laplace transform of g, which is minus g of 0 plus s times the Laplace transform of g of t, like this. But g of t is f prime of t, right? So over here, this naturally turns into f prime of 0 plus s, now the Laplace transform of f prime of t, right? And this we can write down too, based on what we previously did, right? And let's actually do this in green. The Laplace transform of f prime of t is minus f of 0 plus s, the Laplace transform of f, like this. So using this result, we actually have from the above equal sign, f prime of 0 plus s times minus f of 0 plus s, the Laplace transform of f. And if I distribute everything, what this turns into is minus f prime of 0 minus s of 0 plus now s squared times the Laplace transform of f of t like this, and this actually answers our question. Well, so the conclusion is that the Laplace transform of the second derivative of f is equal to minus the value of the first derivative of f minus s times the value of f plus s squared times the Laplace transform of f of t like this. And this is a major conclusion. Now, if you actually carry out the pattern, hopefully you can actually see what the pattern is, and you can actually prove this to yourself as well. So suppose that continuing along with the pattern, you're seeing. We could also say that the Laplace transform, let's say, of the third derivative, f, well, it's going to be minus the second derivative at 0 minus s times the first derivative value at 0 minus s squared times the value of f of 0, and then finally plus s cubed times the Laplace transform of f of t like this. So notice that in each one of these terms, right, in terms of the highest derivative, all three of these terms contain the initial conditions for f, and they all come in with a minus sign. They keep on increasing in order of multiplication of s. The last term is always multiplied by s to whatever order it happens to be times the Laplace transform of that original function. So one of the things that you could actually say as this generalization, and there are various proofs for this, is this is the biggest conclusion, and this is based on following the patterns that we have, is that the Laplace transform, let's say, of the nth derivative of f, well, it's of the form s to the n times the Laplace transform of the original function, this, and then minus s to the n minus 1 times the value of the function at 0 minus s to the n minus 2 times the derivative of that function at 0. They're all minus signs. S to the n minus 3 times the second derivative, evaluated at 0, minus the n minus 1th derivative, evaluated at 0, like this. This is biggest abstract form for that, but I think that based on what you actually see right here, if you ever have to find the Laplace transform of a fourth derivative or a fifth derivative, which is very, very, very rare, you should be able to follow that pattern and actually compute these things. But notice that one of the things that's been done, right, is by taking the Laplace transform of a higher derivative in the time domain, there are no derivatives in the Laplace transform. What you end up with on the right-hand side over here, notice that this is algebraic in S. It is a polynomial in S. And that's the important thing whenever you take Laplace transforms of derivatives. And we'll talk more about this as we go on.